Persistent summer, high electricity costs, and frequent outages may make conventional mechanical cooling unsustainable and unreliable. Passive ventilation, especially the solar chimneys, offer a very low energy solution to enhance the natural airflow, improve the thermal comfort, and reduce the dependence on mechanical cooling. Solar energy is a clean and renewable resource of energy, and it can without and reducing the carbon emissions. Previous experimental studies and CFD-based studies confirm that solar chimney design parameters can significantly enhance airflow performance under the hot climatic conditions. And this research focuses on studies by focusing on design optimization and practical applicability of solar chimney systems for energy efficiency and sustainable um, buildings in semi-arid urban environments. These are the objectives of my research to evaluate the impact of air channel gap and chimney inclination angle and hybrid solar assisted configuration on airflow performance and thermal comfort in semi-arid climatic conditions, to analyze the effectiveness of smart controls and solar aided strategies in enhancing the natural ventilation um, as compared to the mechanical cooling using CFD simulations under the extreme summer conditions. And then at the last, to develop a practical and scalable design guidelines for optimizing the solar chimney system to support the sustainable low energy building designs in hot semi-arid urban environments. Coming towards the research methodology, a CFD-based methodology was adopted to carry out the research. A prototype model of 12 feet by 12 feet was prepared on CFD, Autodesk CFD, and with a south-facing opening, incorporating the solar chimney. And the study systematically investigated the influence of air gap width and chimney inclination angle with stack height varying as a function of the inclination. In summarizing the optimization process, we first prepared the test room, then variation in parameters, especially the air gaps, then inclination angle, and then at the last we selected the optimized design parameter. This is the simplest schematic diagram of all the research which was carried out. A room of 12 feet by 12 feet was prepared. Inlet with the normal sill level was induced. So incorporated inside the room. And the solar chimney has four main components: the glass cover, the air channel, absorber plate, and insulation. These are the specification, the room specification and the physical parameters of the solar chimney. And the length of the solar chimney was 6 feet. The width of the solar chimney was 4 feet. The air gap and the inclination angles were the parameters which was varied to find out the optimized design. The 6 inch width, 12 inches width, 15, 18, and 24 inches width was used for the air gap, and the inclination angle was varied from 30 degree to 90 degree. The component of solar chimney are absorber plate. The absorber plate is there to absorb the heat radiations from the solar energy, and the glazing is here to reflect the solar energy, and insulation is there to maintain a certain air temperature, the highest certain air temperature inside the air gap. The latitude of the Lahore, as you know, is 31, and all the input parameters, which were the boundary conditions for our CFD model, here in the table, these are noted. Research methodology. The study systematically investigated the influence of air gap and the chimney inclination angle with stake height, and three-dimensional steady-state simulation was conducted using the finite volume method with automatic mesh generation and surface refinement to resolve the heat transfer and airflow phenomena. The material properties and the boundary conditions were set for the CFD model. This is the overall scheme which was adopted for the CFD modeling. Coming towards the results and discussion. The CFD results indicates that a 45-degree chimney inclination produced the maximum exit air velocity, offering an optimal balance between the solar heat gain and buoyancy-driven flow. Lower inclination angles, 30-degree, higher solar absorption but reduced airflow due to limited stack height and increasing friction. While the vertical configuration, 90-degree, exhibit the weakest performance because of the reduced solar exposure. Variation of air gap width revealed that a 15 inches gap delivered the highest ventilation efficiency, while the smaller gap restricted the airflow, whereas the larger gaps caused excessive heat loss, weakening the chimney effect. Summarizing all the results these are the graphs. At 30-degree, we have the maximum heat absorption. At 90-degree, we have the minimum heat absorption. This is the variation of heat reflux which we obtained from the CFD simulation. Variation temperature, the maximum temperature is absorbed at 30 degrees because the temperature absorption is depending on the latitude of the location. So 30 degree is the angle where maximum heat absorption is obtained. But the air gap width comparing both the parameters, that is air gap width and heat absorption, we obtained the result, optimized result at 45-degree angles. We are getting the maximum air velocities in the channel, and the channel gap must be between 15 inches.
Farah, you are requested to please conclude your research.
Yes. Coming towards, these are the gradients. We have to notice the gradients as well. At 45-degree, we have a better gradient inside the room, and the airflow is also maximum. Heat absorption is good. So we concluded, and all the results were validated at the with a physical model, and the temperatures were validated with a digital thermometer. This is coming to the conclusion. The study confirms that properly optimized solar chimney can serve as an effective passive ventilation strategy for hot semi-arid climates, significantly enhancing the airflow and thermal comfort. CFD results validated through experimental measurements demonstrated that a 45-degree inclination angle with a 15 inches air gap width delivered the highest exit velocities and most stable airflow, reducing the reliance on mechanical cooling. The optimized system proved effective using conventional materials and local construction practices, highlighting its practical applicability under extreme summer conditions and its potential to the energy efficient and sustainable urban buildings. For the future scope, we can just combine this simplest model with some other pre-cooling techniques such as the earth tunnels and further improve the efficiency of the system. These are the references, and thank you so much. If you have any questions, please.
Thank you so much, Ms. Farah. Very nicely done. Now the floor is open for the questions. Any two questions from the audience? Okay, thank you so much, Ms. Farah. It was nice.
Thank you. Thank you so much.
Now we have a physical puzzle here.